Alright, Advanced Chem students, here we are in the second video talking about alkene reactions with strong acids. In the previous video, I showed you the basic scheme of the reaction and the proposed mechanism. In this video, I'm going to show you the basic scheme of a particular kind of alkene, namely propene, reacting with HCl, and I'm going to show you the mechanism that helps explain the product distribution. Alright, so once again, this top reaction would represent the facts on the ground. If you take propene, this molecule here, and you were to react it, this molecule here, and you were to react it with HCl, here are the facts. This is the experimental observation that we're going to try to explain. What you do is you get a product mixture. You can get the HCl to add to the double bond in such a way that you get two possible products. You can get 2-chloropropane, or you can get 1-chloropropane. Essentially, the H of HCl goes to one side of the double bond, and then the Cl of HCl goes to the other side of the double bond. And so you end up getting either 2-chloropropane or 1-chloropropane. Now, the experimental observation is that you get 95% 2-chloropropane. It doesn't matter how many times you do this reaction, it doesn't matter where you do this reaction, and for the most part, it really is largely temperature independent as well. You're always going to get darn close to 95 to 5, 2-chloro versus 1-chloro. So that's the observation. In the bottom half of the screen, we're going to try to put forth the explanation. And the mechanism I'm showing down here on the bottom is essentially the same mechanism I showed you in the first video, except now it's being applied to the specific scenario of the reactivity of propene. Alright, so let me show you the mechanism. Here's my propene molecule right here. For now, ignore all the arrows that are around it. Here's my HCl molecule. So, as I showed in the previous video, what happens is the pi electrons in the double bond, in this case of propene, are an area that is electron rich. And so they're going to go after, attack, the electron deficient H of HCl, and at the same time, the electrons of the HCl will move over to the chlorine. So we're going to make a carbon-hydrogen bond, and we're breaking simultaneously the HCl bond to leave behind a chloride. But as you can see here, propene is an asymmetric alkene. The carbon here on the left is different than the carbon here on the right. The carbon on the right has one methyl group and one undrawn hydrogen. The carbon on the left has two undrawn hydrogens. So when I make my first carbon-hydrogen bond during this attack, I can go in one of two different directions. I can make the carbon-hydrogen bond located here, the new carbon-hydrogen bond, here at C1, that I labeled C1, or here at C2. And both pathways are open to the system. Let's follow the first pathway. What happens if this electron density in the pi bond is transferred to this hydrogen in such a way as to make the carbon-hydrogen bond here at C1. That's this top pathway. So this carbon forms a bond with that hydrogen. The net result is this CH bond, leaving behind a carbon-carbon single bond and an area of electron deficiency on the other carbon, to which I have yet to add anything. So this carbon here still has these two pi electrons around it, except it's now in the form of a CH single bond. This carbon, that used to be part of the carbon-carbon double bond, now has fewer electrons around it, so it's a carbocation. If I follow the other pathway, and I make the CH bond here at C2, and go through this bottom pathway, now I have the new carbon-hydrogen bond here, located at C2, and C1, to which nothing has been added. The only thing that happened to C1 is it lost out on the electrons that were in the double bond, is now the location of the carbocation. Take a look at these two carbocations in my intermediates. They look ever so slightly different. This carbocation has, this carbon right here has one carbon 2 carbons and an undrawn hydrogen on it. This carbocation here on the bottom pathway has 1 carbon and 2 undrawn hydrogens around it. So we have different kinds of carbocations. If you have a carbocation that is surrounded by only 1 other carbon, we call that a primary carbocation. I'm designating primary by using the notation 1 with a degree symbol on it. That means primary. If I have a carbocation with 2 other carbons around it, that's called a secondary carbocation. Ignore the little space between the 2 and the superscript 0 there. It's not supposed to be there. That's a secondary carbocation. And I don't have it shown here on my screen, but you can imagine if you have a carbocation with 3 carbons around it, that's going to be called a tertiary carbocation. All right, so I have my 2 carbocation potential intermediates, and they're both going to do the same thing that I showed in the previous video. I now have an area of electron deficiency, a positive charge, and I have that newly formed chloride anion that was the byproduct of the first step over here. So now that anionic chloride is going to attack the carbocation, be it in the top pathway, or the anionic chloride will attack the carbocation in the bottom pathway. And the end result here is that in the top pathway, I get the 2-chloropropane. Now, I don't show it in the final product here, but my new CH bond is still there, and then I've made in the second step the new CCl bond. So that's how I get 2-chloropropane. When the chloride attacks the carbocation, the primary carbocation that I'm showing in the bottom pathway, I get the 1-chloropropane. And remember, the product distribution was 95 to 5. 95 to 5. So this must mean, if my proposed mechanism is at all correct, this must mean that this top pathway, bond formation between C1 and the hydrogen is favored over the bottom pathway where we form the CH bond between this carbon and the hydrogen C2. And that is true, and the reason it's true is because secondary carbocations are more stable than primary carbocations. This is an area of electron deficiency, so we want to stabilize it by surrounding it by electrons. Well, carbon groups can bring more electron density to the party than hydrogens can, than the 2 undrawn hydrogens there. So a secondary carbocation, for however long it exists, can exist for a little bit longer because secondary is more stable than primary. And as you might guess, tertiary, not shown here on the slide, is going to be more stable than secondary, which is more stable than primary. So the 95 to 5 product distribution, that is the fact of the matter. That's what the reaction does. That's what Mother Nature does when she reacts propene with the HCl. This 95 to 5 distribution can be explained by us mere mortal human beings by looking at our proposed mechanism, for which we have some other good evidence for, by looking at our proposed mechanism and postulating the possibility that secondary carbocations are more stable than primary carbocations. So, this is the reactivity between alkenes and strong acids. In the notes in the packet that we have, there are other reactions of alkenes. They are all largely a variation on the theme that we're showing here in this particular case with propene and HCl. So if you can understand the essences of this reaction and this hypothetical mechanism, then you should be in good position to understand how the reactivity for the other reactions, hydration, hydrogenation, etc., that are shown in the packet, how those reactions are believed to occur. All right, that'll do it. We'll see you in class.